Hello everyone, I hope you enjoyed my last video on the jerk, the rate of change of acceleration. Well, this video also deals with acceleration, but you'll be pleased to note these are strictly constant or uniform accelerations that we're dealing with here. Here I have something called the Atwood Machine, invented by a man called George Atwood in 1784. It's a device that we can use to investigate all sorts of dynamics phenomena. In this video I'm going to show you how we can use this device to get a value for the acceleration due to gravity. Now, the point being here, in these days our timing devices were rather crude. They were ingenious, but they were crude. They couldn't really measure short time intervals with any real accuracy. And if you think gravity has an acceleration of 9.8 meters per second, this means if you drop something from rest for a mere 1 second, after that 1 second elapses, its speed will be 9.8 meters per second, and it'll have travelled 4.9 meters. Now that's a large change in position, and it's a rapidly changing speed. And to measure this with any real timing accuracy would have been impossible in these days. But this device here shows us how we actually can scale down the acceleration due to gravity to a magnitude that's easy, or much easier to measure. For example, suppose we can scale down 9.8 meters per second to 1.6 meters per second. Well, that's a much slower increase in speed, and over a 1 second time interval it was not going to travel as far, thus making it much easier to measure, especially in those days. There was no technology like mobile phones and cameras that can record 60 frames a second in 1784, so they had to get around that, and they had ingenious ways of doing that, including this device here. So what is this device then? Well, we've got two masses connected to each other over a pulley, and the right hand side, you can see, is slightly heavier than the left hand side due to this tiny wee mass I've got added to it. Let's look at the basic action now. Start. As you can see, the heavier side pulled down the lighter side. One side went up, the other side went down. So how do we use this device then, or this machine, to find the acceleration of a body falling near Earth's surface? In other words, how do we use this device to find the acceleration due to gravity? Well, we need a formula for that. And you know, we don't just pluck formulas out of mid-air. No, we actually have to work them out. So how do we do this then? Well, this is a force question. If it's a force question, we have to use Newton's laws of motion. And notice, we have two bodies. Therefore, we need two coordinate systems, two free body diagrams, and we apply Newton's law to both of these free body diagrams. Then we eliminate, when we have our simultaneous equations, one for each body, we can eliminate the tension, which is the same on both sides, and that will give us a formula for G. First thing we need to do is choose our coordinate system. Well, there's no horizontal motion here, it's all vertical, so we're only thinking about the y direction. Once we've achieved this, we need to think about the directions then. Which direction should be positive and which direction should be negative. Now normally, upwards is positive and downwards is negative. If it did that, it would work. But I'm going to do it a different way, because it means one step less. Now I recommend it, but you can do after the video. Why don't you read the question where the coordinate systems are both positive for upwards? You get the exact same answer, but there's an extra step where you have to utilise the fact that the acceleration in both bodies is the same in magnitude but opposite in direction. Make that substitution and you get the same formula I'm going to show you just now. So what I'm going to do is I'm going to choose positive upwards for the one on the left and positive downwards for the one on the right. Draw my three body diagrams, put in the appropriate physical quantities, then put in their magnitudes and directions, put them together, add them together to eliminate T, the tension, which is the same on both sides, and you get a formula for the acceleration due to gravity. So how do we use the formula then to find the acceleration due to gravity? Well, we'll have to use masses, and we just weigh those, and that's fine. How do we find the acceleration of the blocks? Well, that's quite simple really. All we have to do is this. Focus on the right hand side, the heavy side. Start timing. Allow the blocks to fall for exactly 1 second, and as soon as that second has elapsed, remove the excess block and allow the block to fall for a further 1 second, and see how far the block travels during that second. Note the distance it travels, and suppose it travels say 40 centimeters, then the acceleration is 40 centimeters per second. Think about that. So suppose you have the device and it's perfectly balanced with 100 grams on one side and 100 grams on the other side, and you wish to simulate the moon's gravity, which is 1.6 meters per second. How much mass would you have to add to one of the sides? Well, the answer is 39 grams. How did I get that value? I'll let you think about that. Now, I hope you liked the video. If you did, give it a like. You can share it with your friends, and they may be interested as well. Any comments, please leave them. Any questions you've got, just ask and I'll get back to you. Thank you very much for Esco's Physicist. If you've got any other suggestions for any other videos you think of, let me know. Meanwhile, thank you very much. Until next time.